Now we're going to begin our study of step or forced functions for first order responses. But before we do that, we want to first spend a little bit of time talking about singularity functions. And as we're going to see, singularity functions are a mathematical way of representing a switching event, which, as we have seen, is fundamental to how these first order circuits work. So what is a singularity function? Well, singularity functions actually have an extremely broad range of use in engineering theory, and specifically in signal processing applications. I'm going to give a very quick overview of singularity functions, at least some of the basics, and focus specifically on one that's going to be useful to us in this course here whenever we are looking at how switching events occur. But you're going to see a great deal more of this later on if you take more courses in advanced signal processing. So let's talk a little bit about singularity functions, and let's look at three of the fundamental ones, the first being the unit impulse. Or is it sometimes called as the delta function? So how do we represent this mathematically? Well, the best way to illustrate this is to kind of draw it graphically. The unit impulse is essentially usually illustrated by a thick upward pointing arrow, which is defined right on the time t equals 0 axis. So mathematically, the unit impulse can be described as such. It has a value of 0 for t less than 0. It has a value of t0 for t greater than 0, and it has an undefined value at t equals 0. Now you can look at this and kind of question exactly what is the utility of a mathematical function that is described like this. But the delta function or the unit impulse function has one other very important property. If we integrate the delta function and look at its area just right around t equals 0, so integrate from just before to just after t equals 0, we take the integral. In other words, what is the area under this function? Turns out it's equal to unity. Has an area of 1. Turns out that's an extremely useful property whenever you're doing something called sampling. So it turns out this is true. If you take any function f sub t, multiply it times the unit impulse function, and then integrate around t equals 0, what you will get is the value of that function at t equals 0. We call this the sampling function. This is a fundamental function to many aspects of signal processing, specifically digital signal processing, where you are sampling and taking measurements of some function and then calculating the value at that particular time when you take that sample. So in more advanced classes, you'll spend a great deal of time learning about this function and learning how to use it. But this is not really something that we're going to be using, this particular function. But the sampling, pardon me, the unit impulse function itself then leads to another function. The next singularity function is the unit step function. And the unit step function is represented by u of t. And u of t, by definition, is the integral of the unit impulse function. Although actually I should do this as d tau instead of t. So this is tau d tau. So the unit step function is just the integral of the unit step function. Or pardon me, the integral of the unit impulse function, excuse me. So if we take the integral of that delta function, what do we get? Turns out when we integrate, we get this. We get a function which has a value of 0 for t less than 0. Then at t equals 0, you have a discontinuity to a value of 1. And then for all t greater than 0, it remains at 1. So therefore, u of t is equal to 0 for t less than 0. It's equal to 1 for t greater than 0. And it is undefined at t equals 0. Because there's a discontinuity. So the undefined value. As we're going to see, this is actually a very, very useful function to us. The final function we're going to look at is the unit ramp function. And the unit ramp function, just as the unit step function was the integral of the unit impulse function, the unit ramp function is the integral of the unit step function. And the unit ramp function looks like this. It has a value of 0 for t less than 0. And then at time t equals 0 and thereafter, it has a value of t. So it ramps up. So r of t is equal to 0 for t less than 0. And it's equal to t for t greater than or equal to 0. So these functions are absolutely essential to communications theory. And as I've already said, in other courses you will learn a lot more about these functions. But as far as we're concerned, we're going to focus on the unit step function. And the reason why is this. I've got a function which for t less than 0 has a value of 0. For t greater than 0 has a value of 1. So what if I were to say that the t equals 0 value corresponds to off, whereas the t equal 1 value corresponds to on? Or if t equals 0 corresponds to open, and t equal 1 corresponds as closed. In other words, you could think about how this could mathematically be used to represent a switch opening and closing. And because of that, it gives us a mathematical way of describing when a switching event occurs. So, the unit step function, of course, all of these singularity functions are idealized functions. You can't create a unit step function typically because you can't get a perfect discontinuity. But from an ideal point of view, they work quite well in terms of a lot of the applications we'd like to describe in engineering. So, it turns out this is a very practical tool, and let's kind of look at some of the properties of the unit step function to see how we can use it. So, let's talk about some of those properties. So what are the useful mathematical properties of the unit step function? First is scaling. For example, let's say we have a unit step function which is multiplied by a quantity VA times U of t. So I'm scaling that by this quantity. What we're going to get is something that's equal to VA times 0 is equal to 0 for t less than 0, and something that's equal to VA times 1 is equal to VA for t greater than 0. So what I'll get is something like this. So I scale the output by some value VA. And VA, I mean, this could represent a voltage or some other quantity, and it can be a positive or a negative value. All right? Now notice I still have the discontinuity here at time t equals 0. But before and after, here's where you see the scaling event for t greater than 0. In addition to scaling, you can time shift. So we can define a u of t minus t sub s. And we think about this. This is equal to 0 for t less than t sub s. It's equal to 1 for t greater than t sub s. And so in this case, we have a unit step function that is going to shift at this time t sub s. So it's 0 all the way up to that point. Then it goes to unity value for time t greater than t sub s. Now sometimes people question, well, shouldn't that be a plus rather than a minus? No, not at all. Okay? Because u of x is equal to 0 if x is less than 0. In other words, if t minus t sub s is less than 0 or t is less than t sub s. So that's where the minus sign comes in. All right? So this should be t minus, not t plus. And incidentally, I'm assuming that in your other math courses, you have seen this concept of time shifting before along a time axis. So this is probably nothing new to you. Now, of course, I've got this as t minus t sub s. What if I did this? What is ut equal t sub s? What would that be equal to? Well, in this case, we would shift in the opposite direction. Minus t sub s is where I would transition to a value of 1. And once again, if we think about it, t plus s, if that is less than 0, then u of t plus s is equal to 0. Okay. Well, in this case, what we get then is t is less than minus t sub s for that to be true, right? So therefore, I get a value of 0 if t is less than t sub s. And if it's greater than t sub s, I get a value of 1. Okay? In fact, we can flip this around in a different way. What if we were to take time shifting and scaling and combine them? Well, in that case, let's do this. What is VAU of t minus t sub s? What's that going to be equal to? Well, in this case, I'm going to scale and I'm going to shift to TS. So when you think about it, this is going to be equal to 0 for t less than TS will be equal to VA for t greater than TS is what we get. And so I'll see this. Now I see something that stays at 0 all the way up to t sub s and now increases to a value of VA. So I can combine those properties together. In fact, I can do something else. What is VAU of minus t? All right. So in this case, u of x is equal to 0 if x is less than 0. So u of t minus t is equal to 0 if minus t is less than 0 or t is greater than 0. And so I'm flipping it around. And u of x is equal to 0 if, pardon me, it's equal to unity, is equal to 1 if x is greater than 0, and therefore if minus t is greater than 0 or t is less than 0. So now I'm getting this. I'm getting a function that has a value of VA until it gets to t equals 0 and then goes to a value of 0 for t greater than 0. So notice what we have here. If I do u of t, it's 0 and then turns on and goes to VA for t greater than 0. If I do u of minus t, it has a positive value, then goes to 0 for t greater than 0. So consider what I've got here. Now I've got something that was on for t less than 0, but is now off for t greater than 0. So I flipped this around from the VA u of t I looked at before. So now you begin to see how you can kind of use this idea mathematically as a way of representing a switching event, a switch either opening or closing at time t equals 0. You can even go further than this, incidentally. I just want to mention you can actually make some pretty complex waveforms using the unit step function. So for example, let's plot the following. Let's plot V of t, some voltage with respect to time, is equal to 3 times u t minus 1 minus 3 times u t minus 3. Or you can rewrite this and say this is equal to u t minus 1 plus minus 3 times u t minus 3. So clearly this is the superposition of two different voltages. And one of them is going to look like this. I've got a voltage that is off until it gets to time t equal 1 second, and then goes to a value of 3 volts. And then I've got another voltage which has a value of 0 until it gets to a value of 3 seconds, and then goes to minus 3 volts. So that's this first function, and this is the second function. All right? So here I'm scaled by -3, delayed by 3 seconds. All right? Now I'm going to add these together. Well, clearly for t greater than 3 seconds, the +3 and the -3 are going to cancel each other out. And what I wind up with is this. When I add those together, I'll have this. A voltage that turns on at 1 second, goes to 3 volts, and then at 3 seconds, goes back to 0 again. So what do I get here? I get a pulse. And in fact, I can take this idea and I could, for example, create a whole train of pulses by adding together different unit step functions. And so I could actually go through and do a pulse train like so, just by combining various functions that turn on and off at various times to create those pulses. So all kinds of interesting little functions you can create. You can also, of course, create sawtooth and triangular waveforms using the unit ramp function. So you can actually represent some extremely complex waveforms just by stringing these unit functions together. However, we're not going to really be doing that in this course. Our focus is going to be on the u of t and the u of minus t functions, because we're going to use these as ways to represent a mathematical way of turning a source on or off. And here's a perfect example of that. Let's say we've got this circuit. And this, of course, is very familiar. It looks just like a circuit we were looking at before. Simple RL circuit. And this is a circuit where at time t equals 0, a switch opens up. So in this case, we went through and we actually analyzed the current I sub L and found the function for this, solved the differential equation, and we found, of course, that IL was equal to I0 for t less than 0, assuming steady state. And we also found that IL was equal to I0 times e to the minus r over L times t for t greater than 0. So we went through and did that analysis using a representation of a mechanical switch opening and closing. But what if I drew this circuit? So here I have a current source with a value of I0 U of minus t amps. What do I have here? I've got a source that has a value of I0 for t less than 0 and a value of 0 for t greater than 0. So if you think about it, for t greater than 0, this thing goes to 0, in which case this current source becomes an open circuit. So for t greater than 0, this and this are the same circuit. Over here, I disconnect the current source and it flows through the resistor. Over here, I just zero it out. But both circuits, I'm establishing the same initial condition in the inductor. And so in this case, just as with here, I'll have exactly the same answer for R of L. So this technique of having a current source multiplied by a unit step function gives me a way of turning this source off. And so I'm creating a mathematical switching event as opposed to drawing a switch representation. Now, if you look at the problems you're going to be working through to practice this, you'll see both types of problems. You'll see some problems where a switch is used to create a switching event. You'll see other problems where a unit step function is used to generate the switching event by zeroing out or either activating or deactivating a source at time t equals 0. So this is just kind of a very useful mathematical way of accomplishing that. Okay? So now that we've learned about singularity functions, now we'll step into our very last topic, which is going to be, for this chapter, working through and learning how to do the step function or forced response, and then looking at what we call the general response. And we'll kind of look at both of those together.